Hello everyone. My name is Seonmyeong Bak. I'm PhD student in Pair Program Lab and ChaNGa team. Today I'm going to present my work on the integration of OpenMP into ChaNGa. First, I'm going to introduce the motivation of this work and share the analysis I did to measure the load imbalance and performance of existing periodic load balancing and overdecomposition on ChaNGa. And I'm going to show how we integrated OpenMP into CHAM and show some evaluation results with 3 applications, Lassen and Kripke and ChaNGa. So yeah, the load imbalance becomes more critical issue because we have more number of cores within a node, and pair applications have really variable size of problems and loads over runtime. So usually we use 2 ways to resolve load imbalance within a node. First, we use coarse-grained periodic load balancing to migrate objects across nodes and PEs. But periodic load balancing cannot be called frequently because of increasing overhead. So the other way we use for load balancing is to use hybrid program models such as MPI plus X. So we resolve load imbalance using more fine-grained tasks from task parallelism such as OpenMP. But each process has a separate thread pool, so it has some limitation in load balancing. So first I show you the implementation. I measure the load imbalance and performance with some highly load imbalance application, Lassen. Lassen is a wave propagation application and developed by Lawrence Livermore National Lab. So I ran this application on Curry, Haswell nodes with 2 sockets, 16-core CPUs, and measure the load imbalance of Lassen with this metric. So the bigger value of this metric means the nodes and P's have more load imbalance. So let's look at the result. So I used also for different kinds of load balancing strategies. We have the greedy LB is the most common one, and it moves the load on the heaviest load to the least loaded P. And greedy refined LB is the modified and refined version of greedy LB. It minimizes the migration of charge. And refined LB is to compute the average of P's and make all the P's to reach the average. And hybrid LB is a hierarchical load balancing. So in this hybrid LB, we use refined LB for the first level of the hierarchy and use the greedy refined LB for the second level. So no LB is a baseline, the execution without any load balancing code. So so the left graph shows the load imbalance factor I showed in the previous graph. So as you can see, with higher over-decomposition ratio and more number of chars, we can reduce the load imbalance a lot. So you can see the load imbalance is reduced a lot with more number of chars per PE. And as we increase the frequency of load balancing, we also can reduce the load imbalance. But the reduced load imbalance results in low performance gain. The answer is no. So we also measure the performance of this application with the same configuration. So as you increase the number of chars, you can see that from certain point you can see some performance degradation because of some overhead, such as if you increase the number of chars, then you may have some bigger surface to volume ratio. So you may have some more communication between neighboring objects. And you also have scheduling overhead, and you also lose some locality. So more higher decomposition doesn't have performance from certain point. And if you increase the frequency of load balancing, you also have more load balancing overhead, and you also should spend some migrating costs. So you may not get improved performance from certain point with more frequent load balancing. So this analysis shows that the load balancing, periodic load balancing and over-decomposition has some limitation in performance. So we measure the Lassen and get some detailed timing result. So yeah, in this also detailed timing result, we can see that with more frequent load balancing and higher decomposition ratio, we always get some increasing overhead. So with this analysis, we see that the performance doesn't improve from certain point with just using periodic load balancing and higher overdecomposition ratio. So we use OpenMP and create an implicit task on top of ChaNGa++. So we use user level thread. So these threads can migratable within a node on ChaNGa++ object, here chars. So because this user level thread can be migratable, so all idle PE on ChaNGa+ runtime can steal this ULT from BGPs, which results in just automatic load balancing in marginal cost. So to prevent the unnecessary creation of this implicit task, we used heuristics to minimize the overhead. So we always monitor how many P's are idle within a node and use some historical vector to see how many tasks on each P have been stolen. So this is the diagram and architecture of the integrated OpenMP on ChaNGa++. So when each char encounters OpenMP calls, then the integrated runtime creates user level thread for the OpenMP region. And then they are pushed to the work stealing queue. So here in this diagram, core 1 doesn't have any work on this queue, so it can help other BGPs. So it steals tasks from core 0 and do its work. So if we encounter some barriers, it pushes back the work to the creator's suspended task queue. So in this way, we implemented integrated runtime, and all the barriers are implemented using atomic counter. So actually, for OpenMP, all the threads can be suspended and resumed, but in our work, the method thread here charts creating OpenMP tasks cannot be suspended because ChaNGa++ entry method cannot be suspended. So we use atomic counters for all the barriers in OpenMP here. And I also did some optimizations to minimize the unnecessary internal barriers at LLVM OpenMP runtime. And because this work is based on LLVM OpenMP runtime, it works with intercompiler, Clang, and GNU compiler. And it works on our x86 and power targets. So currently, more directives will be supported and added. So I ran these 3 applications to see the scaling result on Curry and ANL Theta. I used Haskell nodes on Curry, and Theta is a KNL machine. So I use 2 hardware threads per node on both machines. And Curry is only used for Lassen, and I use Theta for all the applications I tested. The first, so I ran Lassen on a single node to see the performance and benefit of this work. So on the left graph, you can see the load imbalance factor reduced a lot. And on the right graph, you can see the performance improvement significantly. So improved load imbalance results in load performance gain here. So we can say that, this integrated runtime works in marginal cost. Then the incurred overhead doesn't outweigh the benefit we have. So this is a scaling result on Lassen. The left graph is the scaling results on Curry Haskell nodes. So we achieve significant speed up over the best configuration we have without OpenMP. So on 512 cores, we achieve 32.5% improvement. And the KNL, we achieved more improvement because KNL has more cores, and load balancing has more effect in performance. So we achieved 45.9% improvement over the best configuration. without OpenMP. And we also ran Kripke. It is MPI plus OpenMP application. So we run Kripke with just normal MP-chain Intel OpenMP and our own MPI implementation, AMPI and OpenMP. So with AMPI, we can run this application using all the cores for all the MPI ranks and OpenMP threads. So we have more freedom to schedule the MPI ranks and threads here. So we achieved better performance and improved some 11% improved over the best MPI configuration on MP-chain Intel OpenMP. So yeah, Kripke shows weak scaling. Finally, we also ran ChaNGa. I used some small input stats, so this input set has some strong scaling limit. So on a single node, we achieved 0.7% improvement, but yeah, the benefit seems to decrease over more number of cores. So yeah, OpenMP work has been available since 6.9. So the initial version was released and presented in ASPM2 last year. And the current work I presented here will be available in 6.9. And it will be presented in May on CC Grid. And we're also working on standalone user level thread OpenMP, which is really similar to Vault, but with different scheduling and different behavior in runtime. So yeah, I'm currently working on this. And yeah, to sum up, I analyzed the limitation of existing load balancing and over decomposition. And I integrate OpenMP to resolve the issue I found on the analysis and show some benefit of this work with 3 different kind of scientific applications on Xeon and ChaNGa machines. So yeah, that's it. Is there any question?
Oh, sorry. Okay. Is this designed to replace the current SMP system that's in Charm++?
Oh, no. It is working on SMP mode of Charm. So yeah, it doesn't replace SMP mode of Charm.
So how is this? Sorry. So how does this integrate with the current SMP system?
Maybe you can show the picture that you had a few slides ago. Well, not this one. Every core runs its own chars, and it can fire off OpenMP iteration chunks, which may be picked up by other cores, which may be doing other work, but when they are not, they will pick your work. Does that make sense?
Yeah.
Oh, okay.
So if I use this with AMPI and I only have one MPI rank per physical core, do I still have the restriction that I can't have globals? Because for our current production code, we have load imbalance where we have basically parts of our computational domain have 100 times as many grid points as other parts. And so we would just like to be able to parallelize those, but getting it to work with OpenMP and MPI and us doing all of that manually is a little bit annoying, but I believe the code does have a few global variables, and I know AMPI itself, if I wanted to have at least more than one rank per core, would not be happy. So does that restriction still apply here?
So this runs in SMP mode. So this runs in SMP mode of Charm. Running with one AMPI rank per core, you still have multiple per process, because you're going to have one process on the node, and then you're going to have multiple ranks for each core that you're running on. So you still have to take care to privatize the global variables.
So I think in our case, the global variables are basically set via initial reading from input files. So as long as I make sure that operation is done, they're effectively const in the sense that they get set once early in the evolution at startup, and then they don't change.
Yeah. So any variables that are only written once and are written to the same value on every rank are fine. But if you're writing them to different values on different ranks, or if you're updating the values, that's where you get into trouble.
Okay, thank you.
So one could imagine you could do the load balancing on, say, an internode level and then use this on a node. I mean, have you tried experiments with that? Or can it be done? And B, have you tried?
That's what it is doing.
But, okay, your plots seem to show that you use no load balancing at all. I'm sorry. All right, I see you do have some with load balancing. Okay.
So blue versus green.
Okay. So the second question with that is that, to which char does the stolen work get attributed to from the standpoint of the load balancer? Yeah. And what's the right answer? I don't know. Do you understand the question? So right, when you're stealing work,
Yeah.
that means that you're the measurement of the work for load balancing, does that also get stolen, or does it go attributed to the original char?
So the measurement, you mean?
Yeah.
So if you steal tasks from other chars, then yeah, so what you're doing is measured on each P, so it'll be contributed to the P stealing the task.
But this is an error, and I was hoping Kavita or someone from the load balancing answer. Okay. Anyone
Yeah.
wants to speak up? Maybe I missed.
Yeah, that's a valid question. It has been discussed in the load balancing subgroup, and we need to attribute it to the correct processor. Right now, I'm not sure we are doing it. So whichever processor executes the chunk, we need to add the load to the original chars load. And I don't know if anyone knows we have already done this or not, but we are planning to do it. And alternatively, you can turn off the OpenMP for a few iterations, measure the load, and then, so that's a workaround.